but you need a little bit more. You need that the components of x to the power s should equal components of x to the power s, where s in u. See, my axiom 1, the thing that was needed to define this category at all, implies in particular that this is true if x is finite. If s is finite. P lower street preserves products, finite products, and so on. But, and finite is typically coming from U itself. It's a discrete thing, relatively discrete thing. But a stronger condition, actually I took it as an additional axiom in the paper that's in the tag. This is needed in order to imply that this is equality. That is to say that the left and right adjoints are the same. Or you don't know what the other adjoint is. The only one you know about is taking the component. But that same functor should, which is manifestly one kind of adjoint, should also serve as the other kind of adjoint. That's the condition that I want to say. To make it equality type. And that's equivalent to this additional sort of continuity condition on the act of taking components. Now, what does this mean? This is false for the usual combinatorial models. Simplicial sets, cubical sets, and so on. It isn't quite true. And that's what really gave rise to the whole industry of equivalent models and so forth, because you have to identify objects a little bit more than they're getting identified by. Of course, many arrows in E are going to become isomorphisms here, because if you have reversed arrows, two arrows back and forth, such that the composites are not necessarily the identity, but just in the same component as the identity, then they will be inverse after you collapse into here. After you go here, they become inverse. Those are what's called classical homotopic equivalences, and there's loads of those. But you need weaker equivalences in order to get, well, you get stronger properties required, of which this is just a little fragment, which interests me. Now, on the other hand, it is true in continuous cases. If we view actual continuous spaces, not just combinatorial models for them. And it's also obviously true in what I think is an important class of things, namely toposes where the Hom sets are finite. Finite graphs, finite dynamical systems, finite autonomy, finite limitation representation, finite groups, finite monoids. There's a vast amount of mathematical information in that particular two category. And there, but very few people have actually looked at the homotopical aspect, the variance of graphs, for example. Just the homotopy category of reflexive graphs is still quite complicated. In fact, I think it's equivalent to the usual homotopy category of all topologicals of CW complex. I think that's right. So, but if the Hom sets are finite, then this is true just because S is finite, and we already hypothesized that in the first axiom. So we'll get a quality type, and a particular quality H, whose values are in that type of quality, associated to every finite automaton, every finite coset, etc. And they will satisfy the property of being a quality type, as well as what it always does is to preserve. It gives another model of lambda calculus, if you want to look at it that way. So if this is true, whether it's because of continuity, or because of finiteness, or because I force it to be true by further equivalent construction, which actually originated in the book of Gabriel and Ziesmann, known as Categories of Fractions in Homotopy So there's three different ways in which this might be true. And that but it's equivalent to the fact that this is a quality type. But it's an extensive quality type. Because H is compatible with the components aspect. I didn't give this a name, but what shall I call it? No, it's the components. Well, let's just call it P bar. This was P, that's P bar. So clearly by construction, P bar H is equal to P in some sense, but in particular, it's for the shrieks. P bar lower shriek, which is the same as P bar lower star, that's what it means to be equality, but that's going to be the same as the components of the original space, general space. In other words, what we're doing is souping up the set of the space of components. We're saying that space of components is not just an abstract set, it's a whole homotopy type. And so it's extensive because it's, by my definition of extensive, is compatibility with the left adjoint, whereas extensive for a quality type, whereas intensive for a quality type was compatibility with the right adjoint, the points. And this, see again intuitively, I don't know exactly to express this in exactly what, but the homotopy, the idea that in the homotopy category, for example, if you have two maps, they're different, they're really, really different. Because it means there's no way to even continuously deform one into the other. In the original space, E, we deform maps into each other. They'd be in the same component of the function space. But after you've passed to the homotopy category, two things are really, really different. So in that sense, we can force it. And we somehow managed to, by twisting words in the most unprincipled manner, we've been able to make a reasonable correlation between extensive and different. So, and actually notice that there are two. This is an important extensive quality. Homotopy type is certainly an important. But there's another one which is valued in the same L. As if we take the substance, going back, remember the substance, the Bose aspect of the substance, rather than the Avogadro aspect. The Q, the construction that we made before. Well, this one, of course, is this one, of course, is now an extensive quality type also. So this is another extensive quality type because it's compatible with the components. Now, the Bose picture had the same components as the original space. It just identified all the points so that the whole component became, there's only one nucleus, so to speak, but it's almost all the same stuff. It's a collapsing to, it's got the same compatibility with P lower shriek. Q lower shriek, or S lower shriek, of course, as P equals QS, and you take the left adjoint, which is so the adjoint's composed theorem in Thomas' paper published 50 years ago, adjoint's composed. And of course, but on the other end, Q lower star is really the same as Q lower shriek because this is quality type. So, and this one has a topos as values. I didn't prove that, but typically the L is also a topos, unlike the Horowitz. So an extensive quality type, an extensive quality whose type is not only a quality but even a topos. By the way, they should have said something more about it. If you take the monoid generated by a single idempotent, or inside S, where S is any given topos, this is a quality type. This is a simple example. If you have a space in which idempotent acts, then the fixed point of that idempotent extracts points, but those are also the components, because everything. Shanuel had this picture about this particular thing. You have all the peasants belong to some castle. Right? So when enemies threaten, then all the peasants run into the castle. A lot of dots, and they all go into some particular main dot, and the main dots are the ones that are fixed. But you can think of it either way. If it's in the privileged class, where's the main point? Duke is the main guy. There's one direct correspondence between dukes and that's one of many ways to think of this. And of course, this is literally the L which arose for the reflexive graphs. In other words, I start off with the graph, pretty complicated, and I come to the simple idea, the graph where everything is a loop. But the latter thing is really equivalent just to a single map that's split, because source and target are equal. So it's really just a set with one idempotent. You draw it differently. You think of the general element as a loop, and then the fixed point as being an actual dot. You could just think of it where all the edges in one set have to be loops. Among those are the degenerate loops. To every loop, you attach the degenerate loop that lives at the loops are degenerate loops. So that's the most general quality is, of course, more general than that. But the example that we have does reduce to the same construction. Essential quality. How do we construct examples? Well, I'm always the axiomatic method, or some computer scientists who were interested in synthetic domain theory. They asked me a couple years ago, what does synthetic really mean? Well, I'm not an expert in where it came from, but what it means for geometry, sine and so on, is that you start like Hegel's statistician started. In other words, you start with the whole thing is already given. You don't know anything about it except that it's given and it has a certain name, which implies something. You don't start by building it up out of nothing into space. Say, it's here, and well, look at it. It has these properties. The properties has all these interactions. Ultimately, I might be able to build it up. It's like the notion of, what did I say, graph mining. Graph miner should not be something that you just build up. You should also know where you're going in a general way. Then you find out through years of work where you're going in a particular way. To know where you're going in a general way is what you should start with, end up with as a row. So it just occurred to me to put Hegel's name there, because that's the kind of thing you do. So if you imagine, I'm in a category of spaces, you start with that. What could that possibly mean? And you look at it more and more closely. And maybe you can analyze it. Well, the way that we always think of building up Rothendy topos, for example, well, you start with sets, and then you have a site, and